Good morning, everybody. Can we officially say the cold is back? Yeah, it's nice, isn't it? I like it. Much rather be cold than hot. Before we get into what we're going to do today, I finally remembered to bring the demonstration I wanted to show you to prove that light has momentum, right? So we're going to do that, and then I'm going to try to convince you that quantum mechanics is a thing and explain all of chemistry in 10 minutes. All right, so a lot going on. It'll probably work the lights on. So what I have here is what we call what do they call this thing? A photometer bulb? No, it's got some fancy name. A radiometer. Anyway, what it is it's a light bulb. So there's a vacuum inside of this glass sphere just to remove any influence or drag from air resistance. And then you'll see it's got this black and white spinny doodad, right, in the top there, like a little windmill kind of thing, right? I'm going to set that on the table. You can kind of see or not see as you choose. But if I just sit it there and I've got light kind of coming from all directions, then it doesn't move. It's sitting on a kind of there's like a metal needle in there, and then it's sitting and it's balancing on that metal needle, trying to give it as little friction as we possibly can. I don't know if you can tell, it's like jiggling just a little bit because of my voice and because of the table moving and because of earthquakes in various places. Who knows why it's moving, right? But the point is, it's mostly just sitting there, not doing anything. I'm going to take I think it's a 40-watt light bulb, okay? And I'm going to shine from one direction, right, this light bulb. And we're going to watch what happens. Right? Okay? So it begins to spin around. We've taken momentum from the photons coming off this light bulb, and we've used those photons to impart momentum to that spinning vane right there. That is a little bit of a lie. There's a little bit of thermodynamics going on here too with heat, but it's a good demonstration of the fact that light does indeed have momentum. This right here is a very old, make sure it's off. This is a very old light that was used on film cameras, like actual film cameras, like home video film cameras. And this is what does it say? 650 watt light. Okay, right? Okay, so it's pretty darn bright. Okay, I don't want to shine it at you because it's really bright light. But just to show that if I get more photons involved, so the brighter the light, the more photons I have, right? The color determines what energy they're going to have, which is related to their momentum. But if I give more photons, then it starts to speed up much faster, right? Okay, so again, Einstein was right. Okay, light does in fact have momentum, and that I'm seeing spots now because this thing was so bright. That momentum can be imparted to physical objects. Just classical idea, right, of having momentum be transferred from one object to another. It's just now light without mass somehow has momentum. All right, so that was just sorry it took me so long to remember to bring this particular demonstration. In quantum mechanics, we often say that we don't understand what's going on, we don't have any intuition about what's going on. What we're talking about is, at least what a physicist is talking about, is we can't explain sort of why it is the way that it is. We have an understanding of the equations, we have an understanding of where they come from, but like why reality is this way, quantum mechanics is not something that we can explain why. Richard Feynman, who was a Nobel Prize winning physicist, he died in 1988. So he was of that generation that didn't quite work on the bomb project, but sort of came a little bit after. He invented something called quantum field theory, quantum electrodynamics, which, if you just think about the words quantum electrodynamics, it's basically the quantum mechanics of electric and magnetic fields. So, hard stuff. That he won the Nobel Prize for. He would go around and he would lecture to the public, and he was famous for his public lectures. And he had this to say in one of them. He said, "What I'm going to tell you about is what we teach our physics students in the 3rd or 4th year of graduate school. It is my task to convince you not to turn away because you don't understand it. You see, my physics students don't understand it. That is because I don't understand it. Nobody does." Which is kind of a brutal way of putting, right? Like, we've got this thing that works so well, but we don't understand it at a level that is intuitive or makes sense to sort of our human experience. As physicists, we understand it mathematically. We understand it experimentally. We understand it theoretically. We can manipulate it. We can make predictions. We can use it. But it's not something that is, well, totally clear, right? No, right? Even to those of us that know how to read the math, okay? So let's try to, I don't know if simplify is the right word here, but let's try to get a grip conceptually on just what the heck quantum mechanics, Schrodinger's equation, and everything is trying to teach us. If I had the right color pen, it would work better. Okay. So Schrodinger's equation gives us not one number like Bohr's model of the atom did for us to keep track of the energy levels where electrons would be. It gives us 3, okay? And the rules that you see here on the screen are rules that are dictated by the mathematics when you treat electrons as waves in a hydrogen atom. We still have that principal quantum number. Still counts 1, 2, 3. But after that, we have some other symbols and other numbers that follow a specific set of rules. And I want to talk about these rules as we go through, okay? And just kind of give you some heads up on what you might see as you read books or look at internet sources. Atomic shell notations is not something that's used very much anymore. Every once in a while it crops up. This really isn't, just about everybody nowadays just uses 1, 2, 3, 4, 5. Every once in a while you'll hear somebody talk about, well, you know, we're talking about electrons in the K shell or the L shell, right? They'll tend to have very gray hair and not know anything about the internet. Okay, most everybody nowadays, inside and outside of physics, just uses the N number. Some chemists tend to use that, but we do use these, right? And if you've taken chemistry, you're familiar with S, P, D, F as these sort of symbols for the different values of L, which again is predicted by Schrodinger's equation. And then there's the nature of spin. Spin is not something that is predicted by Schrodinger's equation. Spin came about due to observations, experiments, and the discovery that electrons, there's a 4th quantum number that is necessary in order to specify where an electron, what energy state an electron is going to be. Excuse me. This is a picture of Niels Bohr on the right and Wolfgang Pauli there on the left. And they are both, well, very old men, staring at a top, at a child's toy. Used to be that you would take a top and you could spin it with your fingers, or you'd have a piece of string you wrap around it and you'd throw it. And the top would spin really fast. I think spin is one of the worst names for, I mean, it's worse than orbital. I mean, orbital's bad enough. But the problem with spin, if I tell you an electron has spin, what's the first thing you think of, like, in your brain? Spins in a circle, spins like a top, spins like a basketball on somebody's finger. None of that is true. That is not what electrons do. Spin is just another address number for an electron's energy state. And I want to make it really clear right now, electrons don't spin on their axes. They don't orbit around things, okay? Electrons in an atom are probability clouds. They're waves. They're standing waves. They don't do anything of the sort. They don't have a definite position. We can only keep track of where they are 90% of the time. And so this name of spin was given because we can measure the angular momentum of an electron, which again is weird. For something that isn't a particle, but is a wave, or both at the same time, it can be weird to talk about its angular momentum. But it's there nonetheless. So what's going on here? This table is trying to indicate something to you about the address, right, that electrons can have. So I want to kind of back up just a little bit and talk about addresses in general. And in quantum mechanics, our goal is to figure out what the energy of an electron is in an atom. That tells us everything about what it's going to do and how it's going to behave. So let's talk about mailing snail mail. What sorts of things do you have to have in an address? Let's say you wanted to mail something to me. It better not be a pipe bomb or anthrax or anything, right? But let's say you wanted to mail something to me, right? What would you have to put on the letter in order to make sure that it got to me? So the person, right? Okay. So let's see. Okay. Followed by what goes on the next line? Okay, so what part of the address is the second? Like, what do you put here? Yeah, there's like numbers and street names and stuff like that, right? Okay, so right? And so what we had there is a street. So we have the person, right? And then we have a street, but we also have like the location on the street, right? Because there could be different, the street's really long, and so there could be, right, different numbers for that street. Okay, what goes on the next line? Okay, so now, right, we're starting to get a little bit bigger, right? So we would do Fresno, California, and then what? The zip code, 937, I can't remember anymore, 41 for campus. So I think campus has its own zip code. So what are the parts here, right? We have kind of the intended recipient, right? And then we have the location on the street. And then on this third line, there's only one thing that you need. I'm not sure that you were aware of this, okay? What's the only thing you need on the third line? It's only the zip code, okay? The zip code is a computer-readable thing. The Fresno, California is just for us humans, right? So if a human had to sort it, right, they would be able to. So an address consists of 4 important pieces of information. Without these 4 pieces of information, even if you got the zip code right, even if you had the street name correct, it still would be undeliverable, right? Unless the person running the post knew exactly where Mr. Awesome lived. So that's what these quantum numbers are in quantum mechanics. These n's, these l's, m sub l's, the spin number, they're 4 parts of a quantum address that tells you where you might be able to find an electron in any given energy state. And so there's rules associated with this addressing scheme. Just like there's rules in everyday addresses, right? What's one of the rules you know about like even and odd numbers on a street? Maybe nobody knows this stuff anymore. Odd numbers addresses are on one side of the street. And where are the even numbered addresses? They're on the opposite side of the street. That's like always the rule, okay? It falls apart with apartment numbers, but generally, okay, if you're going down a street and you look at the right and you see a bunch of odd numbers and you're looking for an even number ending address, you need to be looking on the other side of the street. Nobody does this anymore because Google just tells you where it is, right? But there are rules, right, for laying out addresses. There's rules for how addresses are numbered, right, going down a street, depending on the lot size and all this kind of stuff. Similar set of rules exist for quantum addressing, okay? Where did I put that thing? Right here, okay? And these are the rules that we follow, okay? The first part of the address, the principal quantum number, has to be an integer. And it starts at 1, and it goes every integer up to wherever, okay? The next piece of the address, this orbital quantum number, starts at 0 and terminates at 1 less than where n started. So if our n value were 3, right, then we would do 0, 1, 2. And that's where L would stop. There would be no more L values, okay? If n were equal to 1, then we'd only use 0. Because we can't go up to equal to n. This orbital magnetic quantum number goes from wherever L ends, like if L is equal, like if n equals 3, L equals 2, we would do -2, -1, blah, 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 okay, through 0, all the way up to 2. And I'll show you some examples of those. These rules that I'm telling you for quantum addressing come out of the mathematics of solving Schrodinger's equation. They fall out of the math of making electrons be waves, standing waves, inside of an atom. And then spin ends up being just a plus or minus 1/2 value. The actual value doesn't matter. We could have used red and green or vanilla and chocolate or whatever, right? It's just a label, okay, in there. So just following the rules here, okay, for a principal quantum number of 2, we have, remember the rule, right? So if we start with n equals 2, right, then well, n can take on 2 values. It doesn't just start with 2. Let's come down here. Let's go n, no, let's do it up here. N equals 1, right? So we're going to step through. We're going to go all the way through the first ones, and then we'll let the table take over for the n equals 2 values. So if we start with n equals 1, what can L be? Do you remember the rule? Has to be 0, starts at 0, and goes up to n minus 1, right? Well, n is 1, so L can only be 0, which means that m sub L can only be 0, because m sub L goes from negative L through 0 to positive L. And then finally, we have a spin of plus 1/2, and then we do that all over again. All those values stay the same, but then you guys know what quotes means underneath something? Copy down. Yeah, it's like this symbol, when you put a quote like that, it just means it's the same as the line above it. Okay, so what we find here when we're looking at this is that there are 2 unique addresses that electrons could live at for the n equals 1 set of quantum numbers. Now we'll go to n equals 2. And here we're going to do n equals 2, right? So when n equals 2, L can be 0, but it can also be 1. Right? The rule is L equals 0, 1, 2, 3, 4, 5, counting up the integers. But you have to stop at n minus 1 value. So if n is 2, L can be 0 and L can be 1. Well, when L is 0, ML is only 0, and then we end up with our 2 spin values. So again, for the first part of the n equals 2 set of addresses, we have 2 locations where electrons could live. But if we continue, right, we're still in n equals 2. Now we got to deal with all the L values that are equal to 1. And you'll see there's 6 here. That's because ML, remember, goes from negative L to 0 all the way up to positive L. Okay? So they kind of did it backwards here. That's all right. We got minus 1. And why do we have minus 1 twice? Yeah, we got to take care of both spin values here, right? Okay. So that's why you're going to see these doubled up, right? But L has to be minus 1, 0, and positive 1. Each one of those, right, has a spin that's different, positive or negative 1/2. So how many total addresses are there right here? 6. And how many total addresses are there right here? 2. So what is the total number of addresses in the n equals 2 configuration? It's 8. The first one, there were only 2, right? So in the first energy level, there were 2. And in the second energy level, there were 8. And we can continue this set of rules, applying these rules over and over and over again to determine how many addresses there are for an electron. In quantum mechanics and in chemistry, these addresses are referred to as states, right? You might have heard of shells and things like that. These L values, 1, 0, and negative 1, those tell you like what orbital type it is. When L is equal to 0, you guys can't see me zooming in. When L is equal to 0, that's an S-type orbital. When L is equal to 1, that's a p-type orbital. When L is equal to 2, that's d, so on and so forth. Okay? So that's where those kind of letters come in. And in the end, what we have is a different set of energy levels than we had in the Bohr model of the atom. The Bohr model was just a ladder, right? And it had those certain energy levels, and you just went up the ladder, and basically every rung of the ladder was a place for one electron to be. In the modern quantum mechanical model of the atom, the ladder, well, it doesn't look like a ladder anymore. I like to think of it as a cup or a beaker that I'm filling with electrons. Like you're pouring electrons into this energy well that is the atom. So in this picture, the nucleus of the atom would be way below the bottom of the cup, okay? Way down here. But the first energy level, the ground state that an electron could end up in, would be in this 1s level. Why 1? Well, it's n equals 1, the first energy level. Why s? Well, that's because L is equal to 0, which is an s-type orbital. And we know that an s-type orbital has that spherical symmetry. Looks like a basketball. So as we go to fill our cup here, right, as we put electrons into atoms, the very first electron that we would add would come in and assume a spin. Now there's something called the Pauli exclusion principle, which states that no 2 electrons can have the same spin when they're in the same quantum address. So if our first one goes in as spin up, and that's a convention, we always, if there's just an electron going into an energy level, we usually write it as the spin up one. It actually doesn't matter if that's true or not. But if I add the second one, what am I forced to do? It has to go spin down. And those are the symbols that we use. They're like, it's like an arrow where we don't complete the arrowhead, right? Because that would mean having to pick up our pencil and go back and do it, right? Okay. So spin up, spin down. Those are paired in there. So here's another thing that's different from the Bohr model of the atom. Every one of these rungs, every part of this, certain levels of this cup, is home to 2 electrons. So 2 electrons can exist in the first energy level, and we know that the orbital type is s. When we go to the second, again, obeying the rules of the quantum addressing, we ended up with the 2s. We saw that right here, okay, as we applied the rules, we had like this subset here where L was equal to 0. That's another S-type orbital. It's got higher energy because it's an energy level number 2. But then we also have to take care of these 6 right here. Well, in this picture right here, I could start, right? Again, I'm just sort of filling electrons into atoms now, okay? And then as I fill them up, okay, they would fill in such a way that eventually we would fill up all of those quantum addresses, and then we'd have to start filling the third energy level, and so on and so forth. But how does this explain one of the world's weirdest things ever? Okay. It sucks that this room doesn't have a periodic table in it yet. We're working on it. Apparently, we have 2 big black TVs that don't work, but we don't have a periodic table. Okay. So I apologize. You're going to get a little bit dizzy as I flip back and forth, right, between this periodic table and this cup that I have here. Okay. So let's start with hydrogen. Right here. The atomic number of an element tells you how many protons there are in the nucleus. And on this periodic table, that atomic number is the number in the upper left-hand corner there. Okay? So if we look at hydrogen, it's got an atomic number of 1. And that means there's 1 proton in the nucleus. And how many electrons would hydrogen have if it were neutral? 1, right? 1 proton, 1 electron. That will make it neutral. So that 1 electron in its ground state, perfectly neutral, woo, sloppy handwriting, would end up right there. Okay? Now, is that where hydrogen's electron always has to be? No. It can still be neutral hydrogen, but it could have the electron in an excited state. If it were in an excited state, it could be up here, right? Or, wherever. It could be up here. It depends on how much energy it got, right? Okay. And if it comes crashing back down, releasing a photon as it does, we'll either get the Lyman series or the Balmer series or whatever. Okay. But the point is, normal ground state, neutral hydrogen, this is where its electron would be. So we go back to our periodic table, okay? And now, so we're here at hydrogen, and then to get to our next electron, we have to add a proton to the nucleus, but add another electron to make it neutral, okay? Helium has an atomic number of 2. Where does that second electron go? Into a 1s orbital. Now something strange has happened. I know there's something in between here. I'll get to that in a second. Something strange has happened, right? We were on this side of the periodic table. Now all of a sudden we're over here at this side of the periodic table. And we're about to transition to go to lithium with its 3 protons and hence 3 electrons. But in order to do that, in order for lithium's third electron to come in and live in this quantum apartment, it can't go into a 1s orbital. Why can't it go into the 1s orbital? It's filled up. There's no more room in that spot. Okay? So it has to park in the 2s orbital, assuming it's in the ground state. What has happened on the periodic table? Notice hydrogen and helium, what energy level were their electrons in? The first one. And they happen to be on the first row of the periodic table. With lithium, we're starting to fill the n equals 2. So what row are we on? The second row. And notice there's 2 slots right here, and there's 6 slots right here. Where did the shape of the periodic table come from? Quantum mechanics. periodic table is a visualization of quantum mechanics. We can look at the table and instantly know, for example, let's do strontium, okay? Strontium sitting right here because of its location in the table, okay? 1, 2, 3, 4, 5 rows down. What's the n value going to be? 5. Okay? And because it's in this block of the first 2, what kind of orbital is it going to be? S. I can tell you it's in 5s just by looking at its location on the periodic table. Strontium. How many electrons are in strontium's n equals 3 energy level? So remember, each one of these is filling up an electron, right, as we go. Okay? But for strontium, we got to fill all the way across till we get to here, right? And my question was, how many electrons are there in the third energy shell? 1, 2, 3, 4, 5, 6, 7, 8. Okay? Now I know some of you are going, well, what about these, Mr. Okay, we're going to get there, don't worry. Okay? But as far as the outermost energy levels are concerned, the answer would be 8. Okay? So what's going on here, right? We are filling this cup, right? After lithium comes beryllium. Don't ever be near beryllium. Beryllium's bad news. It'll give you berylliosis, which basically will dissolve your lung tissue. Not a pleasant way to die. I know this because I had to work with some beryllium in graduate school. It was worse than the uranium I had to work with. Okay. After beryllium comes, I can't remember anymore. Boron. They both start with B. That's the problem. Boron, carbon, nitrogen, oxygen, in that order. Boron, carbon, nitrogen, oxygen, fluorine. And then we are going to finally hit the 8th electron in this n equals 2 shell right here. Okay? So when we do that, when that 8th electron goes in, and it's right over here, then we get to neon. Neon is in a column that we call the noble gases over here. Okay? They're not noble because of their parentage or anything like that, right? They're noble because they have complete energy shells. Their p orbitals are completely full, which means they don't like reacting with anything. They're pretty chill. They just won't combine. You can force them to do stuff, but they really don't want to do it. Okay? So with that full energy shell, our next choice to get to the next element, sodium, we have to go down a row and go all the way over to the other side of the periodic table. In this diagram, sodium's electron would end up right there. So when Dmitri Mendeleev sat down to organize the elements into a table that took advantage of the elements like reactivities, what they liked to combine with, if you take a look, I wish I had a picture of Mendeleev. Like physicists get a bad rap for like crazy hairstyles. Have you looked at the chemists throughout history? I mean, like seriously, like grooming is an issue. But Dmitri Mendeleev, like his hair, I think, was like roughly spherical between his head and his beard, right? Anyway, this is how crazy this is. Imagine you are being asked to organize a library, right? You got a bunch of books, and you got to organize them so people can find them. Like, what are all the different ways you could organize the books? Like, how could you sort them and put them in order? You could do it by what? Genre. right? The fiction over here, the nonfiction, all that kind of stuff, right? Okay, fine. Within a genre, what would you do? Okay, you could alphabetize by title. You could alphabetize by author. All the A authors go first, and then you would, within there, if you got an author has several books, you organize them maybe by alphabetical, by title. But those aren't the only way. That's typically how libraries do it, right? It's not the only way. You could organize all the books in the library by the color of their covers. All the greens go in one place, all the blues go in another, right? It would be aesthetically pleasing, but forget being able to find anything. But it is an organizational tool, right? You could organize the books by publishing date, right? Earliest ones go over here, and then the future marches on. So there's lots of ways to organize, right? So let's say that you decide to organize the books in your library the way the Dewey Decimal System does it, which is there's genres, and then within those genres you alphabetize by author, and then within an author you alphabetize by the title of their book. And then you assign some weirdo numbers to it, and you teach kids how to go find things in the library. But that's okay. Nobody uses libraries anymore, right? Except as places to get on the computer. So imagine you did all that with your collection of, let's say, 118 books. And when you did that on your bookshelf, okay, you finished organizing them alphabetically and on whatever, okay, you step back and you look at your bookshelf and you realize that every book that is like 6 books over from the left, and you look down the column, you see that every book has a blue cover. And that as you look at the second row, all of those last names start with the letter D. Like, you'd be a little bit tripped out, wouldn't you? You'd be like, whoa, man, something crazy is going on here. That's basically what happened to Mendeleev in the periodic table. He was organizing elements, and he was lining them up based on like the reactivities. There's lots of different ways to organize the elements, but the way Mendeleev did it, he organized them and then had this weird shape pop out. Mendeleev's table was pretty darn close to this one. Okay? It's just there were some blanks in it. And so what Mendeleev was able to do is based on the blank spot. So like he had all these lined up, but this spot was blank. Germanium right there. He had silicon above it, he had tin below it, he had gallium right there, he had arsenic. But like arsenic didn't line up with silicon, it was better off in the column with phosphorus and all that kind of stuff. So he knew that there was a missing element somewhere. They had 31 down, they had 33 down. Where's the atomic number 32, right? So Mendeleev predicted the properties of germanium. Does anybody know what germanium is used for today? It's everywhere. Pretty much everywhere now. People in third world countries can get electricity to charge their cell phones because of germanium. Yeah, you need a little bit of sun and some germanium layers along with some silicon in order to make a photovoltaic cell or a solar panel. Okay? Mendeleev knew what the properties of this material needed to be. I think it was like 30 years before somebody would actually isolate it and discover it, all because he organized his elements according to the properties that they had. The properties that those elements had, they have them because of quantum mechanics. And the shape of this table is the shape of quantum mechanics. It's Schrodinger's equation given a visual solution. So again, let's just hammer home kind of what these patterns are, okay? In these first 2 columns right here, you are guaranteed that the outermost electron will be in an s orbital. Because in the first 2 columns, home run, they're all s's, okay? Where do all the p's live? Here's all your p orbital stuff. How do we know those are p orbital things? How many columns across are there? It's 6 all the way across, right? And there's always 6 locations, 6 addresses for an L equals 1 or p orbital. All right, then here in the middle, we have a collection that is 10 columns across. Where does the 10 come from? There are 5 different bars here. Again, this comes from L equals 2. And the M sub L goes -2, -1, 0, 1, 2. That was 5 different locations, each of those 5 locations having spin up and spin down for a total of 11. Remember, each one of these lines here represents home for 2 electrons. So in a D-type orbital, there's home to 10 electrons. And then why is there a collection of 14 down here? It's the F-type orbitals. In the F-type orbitals, there are 7 lines, each one of home for 2 electrons. That's a total of 14 electrons that can live in there. By the way, this periodic table, minus all the colors on it, will be the periodic table that I'm putting on your exam. I'm just going to give you the whole periodic table because I expect you to be able to tell me the quantum address of any element on this table. If I give me a number between 1 and 84. 6? 6, 7. Well done. Okay, fine. We'll do both 6, 7, and 67. Okay, so carbon is number 6. Knowing exactly where it is on the table, its outermost electron is in what kind of orbital? P. Has to be a P. Why is it P? It's in the P block, right? What N value? 2. How did you know that? It's on the second row. Okay. What about nitrogen? 7. N equals 2, right? And it's a p-type orbital because it's in the p block. All right, 67. Where's 67? Oh, we're going to cheat. We're going to go down here. Okay, so what is the orbital type for polonium? The orbital type that its electron is in? What block are we in? We're in the F block. Okay? And now it gets tricky. Okay? That's because quantum mechanics follows the rules exactly. And you may or may not have noticed on this kind of cup that I have here, this well, do you see how we have one S and then we have 2S and 2P. In the third energy level, we have SPD. Notice that you don't have F yet. In order to be in the F, we have to be in the 4th energy level. But something kind of weird happens. Do you see how this 4S sneaks its way down, right, below the 3D energy level? Schrodinger's equation tells us that the 4S orbitals have a lower energy than the 3D orbitals do. I don't make the rules. I'm not. You can take this up with the management. Okay? I'm just the messenger, right? This is the way that the universe has been put together. So that's what this picture is for, okay? If you follow this, you'll follow the order of all the orbitals, okay? And you can just, what you do is you start up here at the corner and you work your way along diagonals, and then you come up here and you keep working your way down a diagonal. You come up here, work your way down the diagonal, work your way down the diagonal. I won't provide this for you on the exam, but it's actually stupid easy to come up with. This is what you do. 1S, 2S, 3S, 4S, 5S, 6S, so on and so forth, 7S, right? You just put all the S's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever, all the way down a column, okay? And then, is there such a thing as a 1P? It can't exist because of the rules of quantum mechanics. So we'll start 2p, 3p, 4p, 5p, 6p, 7. Using my handwriting gets really messy at this point. 3d, 4d, 5d, 6d, 7d. And then finally, the F's will be 4f, 5f, 6f, 7f. You could continue with the pattern if you wanted to, but typically this is enough. And then you come along and you just draw diagonal arrows from upper right to bottom left all the way through like this, okay? And then you just read it, right? You start with 1s. What comes after 1s? 2s. What comes after 2s? 2p. What comes after 2p? 3s. What comes after 3s? 3p. Then 4s. So we went 1s, 2s, 2p, 3s, 3p, and then the next thing we run into is a 4s, right? What comes after 4s? 3d, 4p, 5s, and you can kind of just continue this on, right? What you have here is something called an electron configuration. I expect you to be able to tell me the electron configuration of anything on the periodic table. And again, it's kind of drop dead easy if you've got this picture right here. Okay? So let's go back to carbon. And then I'll try to pull off polonium for you. Okay? It's been a long time since I've done an F orbital. It'll be fun. Okay? So carbon has an atomic number of 6, right? If we go back to our electron configuration here, right? For carbon, right? We know we have to get to 6. Well, 1s, how many electrons can I put into 1s? I can put in 2. And the way we indicate that is with a 2 subscript. It's not 1s squared. We say 1s2. All right? 2s, how many electrons can I have in there? 2. It's an s orbital. It has room for 2, doesn't it? Okay. How many electrons do I have so far? 4. So what's the next thing we're going to write down? 2p comes next, right? But we only have 2 more electrons for the carbon, right? So we're going to do 2p2. That would be carbons, right? And I can look at that. I could either follow the pattern or I can just look here. It's in the second row, and it's 2 electrons in the p block, right? 1s2, 2s2, 2p2. All right? What about nitrogen? Nitrogen had 7. Okay? So what do we start with? 1s2. What comes next? 2s2. Then what? 2p3 for the total of 7, right? All right, let's do polonium. Polonium's number 67. Oh my gosh. Okay, so there's a way to shortcut this. Okay, right? Let me show you how to shortcut this. Polonium, technically, this is a really hard example, by the way. Okay, I would never ask you to do this. Polonium's in this row, which would actually be right here. Okay, this 57 to 71 fits inside this box right here. Okay, it's just because of the way that paper is formatted, we can't. Periodic table should be really long and spread out, but it's not. So it has to sit inside here. So what row are we on here? 1, 2, 3, 4, 5. We're on the 6th row, right? Okay. So we know that we're going to have like a 6s2 right here, right? And then we're going to hit the 4f's, right? And how far are we going to go into the 4f's? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I know I end up with 6s2, 4f11, right? Like I know that's my ending. Okay. Let's see. Yeah, and how did I know it went 4F? So here's 6S, and do you see how the next one is 4F? Right? That's how I knew it was going to be a 4F. But everything that came before this sixth row here, right? All of this stuff, right? Coming all the way down to the sixth row. Xenon, okay, is the last noble gas before we get to the sixth row and start filling up the electron configuration for polonium. So one way that we do this is we cheat. And we just put in brackets, we put the symbol for xenon. What that means is the electron configuration for xenon, whatever it is, right? And then 6s2, 4f11. On the periodic table, you do have to be careful. If you're in the D block, let's take molybdenum right here, okay? It's on the fifth row, isn't it? 1, 2, 3, 4, 5. But molybdenum, that is a 4D address. So when you're in the D block, you subtract 1. So D is n minus 1, right, for the actual number that you have. Okay? For F, it's n minus 2. Right? So that's how I knew when I looked here, right? I was on the sixth row for polonium in this part of the table. I subtracted 2 to get to the 4F. So these are the 4Fs, and these are the 5Fs. And I keep screwing it up. Yes, there is a periodic table of meat. There's a periodic table of everything. Chemists are weird. Okay? This is, of course, a joke. But it is one of the most clever jokes I've ever seen in my entire life. I apologize if you are a vegetarian or vegan. Right? But there's some things you just need to understand about the way chemists operate. You will notice that hydrogen, the place for hydrogen, which is like the simplest form of all elements, right? The most basic meat, according to this person, is bacon. That's because bacon, like lasers, makes everything better, right? Okay. Followed by hamburgers, right? And then there's a bunch of other things on here. The thing that's hilarious to me is that they got the noble meats, right? Hamburger, sausage, sloppy joes, fried chicken, barbecue chicken, pepperoni, and hot dogs. Right? These are the meats that you really don't have with anything else. They are a meat unto themselves, right? Okay. They've organized them by mixed. I love that. Gumbo. Seafood up here, right? Red meats take up a more, right? Cold cuts are this section right here. Somebody took a long time to come up with this. It's hilarious. And then like it gets even funnier, right? Okay, without bacon, the world wouldn't exist. Okay, the two basic forms are boned and boneless meats, right? So if you have an H2B, there's B, there's H2. What's an H2B? It's a bacon double cheeseburger. This explains a lot, right? Does anybody know what a turducken is? It's a turkey that's been stuffed with a duck that's been stuffed with a chicken. I've made 2 of these in my life. Okay, it's really hard. You have to debone a chicken, a duck, and a turkey. And shove them into each other with layers of stuffing in between. It's not easy. My wife was disgusted. I thought it was the best thing ever. Right? But notice the turducken, T-H-R-E-D. Can I even find them on this periodic table? I haven't done this in a while. Where's TH? It's somewhere on here. But TH was turkey, RE was duck, and I think, D was duck, and RE was like chicken or something like that. I just think FRCIB. What's FRCI? Fried chicken. Where's CI? Is that chili? Number 17? Yeah, chili. And B, bacon. Fried chicken with chili and bacon is a heart attack, right? So, anyway, this concept and idea of organizing, right? Something we humans love to do. the particular organization of the periodic table is a direct consequence of all the quantum mechanics that was forced upon physicists, right? As we came to grips with, what's an electron? Like, what the heck is it? Sir William Lawrence Bragg, who was a British physicist knighted for his work, I believe he won a Nobel Prize too, he said, the electron is not as simple as it looks. I think that's the understatement of like the century right there, because it can get quite complicated. As for like what I could ask you to do on an exam when it comes to quantum mechanics, like be able to give me a correct electron configuration for any element on the periodic table. You know the rules, should be pretty easy. I won't ask you F's. I might try to trick you with a D, but that's if I'm being really, really mean. Let's do a couple others here just to point out some ideas that you guys may not be aware of because of your chemistry teachers. Could carbon have an electron configuration of this? Is that an allowed configuration? Yes. Have we broken any of the rules? What's going on here? What's happening in this electron configuration? One electron has jumped up. In other words, one of the electrons is in an excited state. I'm not saying this would ever happen. I'm just saying that this is possible and a allowable or correct electron configuration for an excited state of carbon. Okay? For nitrogen, is that allowed? No. This one is impossible. Why is this one impossible? Because the 2s can only have how many electrons in it? 2. S can only ever have 2. I put 3 here. That completely breaks the rules. This is not our universe. Okay? So if I wanted to do an excited state equation, instead of the 3 here, I would put 2 and I could put 4 right there, right? Okay? To indicate that that first electron that was in 1s1, right, hopped up. Did I get the right number? 4, 5, 6, 7? Yes, I did, right? So just kind of be aware, right? You can have excited states where electrons aren't in their ground states. They're higher up. But as long as you're obeying the rules, it's perfectly allowable to happen. I'm not saying it does happen in nature. I'm just saying that it's an allowable quantum address. So if you learn the rules of the quantum addressing, whether you do it from this cup or following this crazy stuff or my preferred way, just follow the periodic table. You should be able to write down the electron configuration for anything. I guess technically, there's some periodic tables that put the electron configuration on there for you. Okay? I guess if you wanted to put that on your cheat sheet, fine, I don't care. You can put whatever you want, right? But you really don't need it, because I'll give you this one and you'll just be able to go, oh, nickel? Nickel's a 3D3. Or, sorry, 3D, 1, 2, 3, 4, 5, 6, 7. Right? Yeah, just nickel sitting right here. How do I know it was a D? It's in the D block. How did I know it was 3? Well, it's in the 4th row, but I have to remember to subtract 1. And then 1, 2, 3, 4, 5, 6, 8. I can't count. Right? So, in some senses, quantum mechanics can be that easy. But in a lot of ways, we don't understand why it is the way that it is. What chemists will do with this is they will run with these rules, these ideas, and then start doing some amazing work in what happens when you start putting elements together. At this point, physicists get bored. We could care less about molecules, right? They're around, they cause problems, whatever, right? But chemists get offended when we say stuff like this. Chemists are applied physicists, right? They are applied quantum mechanics. and they can put together, in pChem, they put together elements into molecules, forming molecular orbitals. It gets really wild, and the math gets really complicated, and it's really cool. And that's the reason we have the kinds of batteries we have today and the different materials that we have today. The art of material science is just absolutely phenomenal, and it's all applied quantum mechanics. In organic chemistry, you're dealing with carbon and really how it connects to just about everything else. I know I greatly oversimplified that, right? But again, it's an applied quantum mechanics. It's just you tend to have organic chemists and physical chemists, and the two don't like talking to each other very much. Because one's scared of the other. Actually, they're both scared of each other. It's pretty funny. Pretty funny to watch. Quantum mechanics makes me fall behind. Lasers work because of quantum mechanics. There. That's all I'm going to say about that, because I want to get started. I will not ask you about lasers on the exam. How's that? Okay. I do want to get started into radioactivity, though, because we have to, on, I think, this Thursday, we're actually going to do a sort of a mini lab exercise in here. I know it sounds weird. We should probably do it on Monday, but I got other plans for Monday. So, but we are going to do like a mini lab in here, and I need to lay down the sort of groundwork, right, for what's going on. The next two chapters, the final two chapters of your Physics 2 career. Congratulations, by the way, surviving this far, right? You've got this. It'll be fine. The last two chapters of your Physics 2 career are going to focus on nuclear physics and cosmology. So the physics of the exceedingly small and the very big. So what we're doing is we're leaving electrons behind. Electrons will come in and out of the picture every once in a while, but we're going to leave electrons behind, and we are going to dive into the nucleus, the region of protons and neutrons, and try to figure out what's going on in there. And this is the region of the very small, right? This is a table that shows like masses of things. And one of the things we start doing, especially in nuclear physics, is instead of using kilograms, which you can see here, all of these masses are like incredibly small, 10 to the minus 27, right, for these protons and neutrons, all that kind of stuff. Instead of dealing with kilograms, which you can do, we instead work in units of atomic mass units. It's that U that's sitting right there. And there's a conversion factor for this. I can never remember what it is. Yeah. It's 1 point. This is going to be weird. It's one atomic mass unit is 1.660539 times 10 to the minus 27 kilograms. And the reason that's weird is I wrote down every significant digit we have for that conversion factor. Normally, I'm not a big significant digits guy. I'm like, this is 1.7 or close enough to 2 that I don't care. But in nuclear physics, all of these significant digits matter. In nuclear physics, we're talking about very small differences in mass between things, and it's those really tiny differences that cause all of the effects that we're going to have in nuclear physics. So when you are doing calculations and you're being asked to convert between atomic mass units and kilograms or whatever, or just one atomic mass unit and another, use as many significant digits as they give you in the problem. It's really important. Otherwise, the round-off error is going to kill you. Okay? So that's why, do you see how on this table right here, they're just carrying out a lot of things. Like even this one, they used 606 significant digits right there to indicate what the heck is going on, right? So the weird thing is the atomic mass unit is defined as carbon's atomic mass. Carbon has an atomic mass of 12, and we define the atomic mass unit to be basically 1/12 of the mass of carbon. And then everything else is scaled according to that. I should point out, carbon so If we look at the periodic table, I really need a periodic table in here. Okay? If we look at the periodic table, what's the atomic number? 6. And you probably can't read it, but down here at the bottom is a mass of 12.011. So when we go to write down the nuclear symbol for carbon, we'd write the number. We put the atomic number as a prefix, but it's a subprefix. And then we put the rounded atomic mass as a superscript in front of it. Okay? So, and we refer to this as carbon-12. That's because there's other kinds of carbon out there, namely one that you've probably heard of, carbon-14. Now, carbon-14 has the same atomic number. The atomic number of an element dictates the element that it is. Anything with 6 protons in its nucleus is carbon. However, these two carbons differ by the number of neutrons in the nucleus. And the way you figure out the number of neutrons is you subtract the mass number from the atomic number. So what's 12 minus 6? 6 neutrons, okay? But carbon-14, what's 14 minus 6? 8 neutrons, okay? So carbon-14 is an isotope of carbon-12. That term isotope means it's the same thing, but it has a different number of neutrons in the nucleus. In fact, technically, they are isotopes of each other. Right? They're the same thing with differing numbers of neutrons. Carbon-12 is the naturally occurring stable version of carbon, meaning that if we went and just got some ashes out of a fireplace or something, out of a campfire, and we started measuring what the carbon is in that ash, we would find that a very high percentage, 99% of that carbon, would be carbon-12, with a smaller amount being carbon-14 and a couple of other isotopes. So the mass that you see on a periodic table is not rounded. Like, again, carbon's was 12.011. That mass is it's a statistically weighted average of all the isotopes that are out there. Carbon-12 is the most abundant isotope. And then carbon-14, 13, and some of the others, they have much rarer occurrences in nature, and so they don't affect it as much. But that's why it's 12.011, right? The average has been not calculated as a straight average, but as a weighted average. What's the other mass that you see on this table that's very, very strange? Mega electron volts per c squared. Where did that come from? It came from Einstein. Remember the rest energy? If you solve for a mass, you get an energy per c squared, right? If you let that energy be in units of mega electron volts, and you divide by c squared, you have a mass. So nuclear physics will actually use mega electron volts per c squared as a mass. And you'll see it, okay? The conversion there is that one atomic mass unit is also equal to 931.494, again, using as many sig figs as we can, mega electron volts per c squared. So these are just conversions, right? Unit conversions for nuclear physics. The nucleus is, I guess it's a collection of balls, right? Protons and neutrons, again, do have wave-particle duality. So they have wavelengths, right? But electrons are exceedingly smaller. Like they're like 1,000 times less massive than a proton or a neutron. And so electrons very often express their wave-like nature. In the nucleus, generally it's safe to just think of them as particles and like nestled spheres that are all sitting together. In this picture, the red ones would be protons and the gray ones would be neutrons. Okay? Only there's a problem with this kind of configuration. Okay? If we go back to the very beginning of this course, what happens if you try to put two positive things together? They repel each other, right? The separation distance between protons in a nucleus is measured in like femtometers, 10 to the minus like 15, 16, 17 meters, right? Really, really close. And if you remember Coulomb's law, the force goes as the inverse of the distance squared. So you got to take a really tiny distance in the denominator and square it. What happens to the force? It gets huge, like impossibly huge, like so big that a nucleus should fly apart. It should not stay together if the only force that were acting on the nucleus was Coulomb's law. Lucky for us, I suppose, in our universe, there is another force. And so, of the fundamental forces that keep our universe together, you've learned two so far. You've learned about Coulomb's law and, gravity, which we now know is no longer a fundamental force, right? But we'll let it sneak in for historical purposes. Okay? So, Coulomb's law, gravity, the third of the fundamental forces is the force that holds nuclei together. We need a name. Does anybody know the name for this one? Strong nuclear force. Why is it called the strong nuclear force? Because physicists at this point lacked any kind of imagination. It's stronger than the electromagnetic repulsion trying to force the nucleus apart. The strong nuclear force, we're not going to give you the math for it because it's pretty complicated, but it acts between all nucleons. So the strong nuclear force acts between neutrons and neutrons, neutrons and protons, protons and protons. As long as you are in the nucleus, you're a neutron or a proton, then you will experience the strong nuclear force. It's that strong nuclear force that keeps nuclei together. Electromagnetism wants to rip the nucleus apart, but it's just slightly weaker than the strong nuclear force. As long as you're small enough. The strong nuclear force, as strong as it is, has a really, really short range. After about 10 to the minus 15 meters, the strong force stops working. So in other words, there will be no strong force between my hands. It's just too far apart. The strong force only works across the nucleus of average to small atoms. If the nucleus gets too big, if there's too many neutrons and protons, then what happens is these charges, these protons on one side and these protons on the other, they're repelling each other. Coulomb's law is infinite in its range. It's not limited at all. Okay? But there's no more strong force that's holding anything together, right? The ones over here and the ones over here don't experience any strong force from the opposite side. They'll feel forces from their neighbors. But now we're running the risk of the electromagnetic repulsion being able to rip this nucleus apart. And that's exactly what happens with anything that has an atomic number larger than 82. Atomic number 82 is lead. Lead is the last of the naturally occurring elements that is naturally stable. Anything with an atomic number bigger than 82 is going to be naturally unstable, meaning that the strong force will have trouble keeping that nucleus together. And when the electromagnetic repulsion wins and the nucleus decays, you end up with radioactivity. An unstable nucleus is one in which the strong force has lost, and you're going to get a radioactive particle out. We'll pick up the story of Marie and Pierre Curie next time, right? As we deal with nuclear binding energy, where radioactivity comes from, and what it means to measure the half-life of a radioactive element. I'll see you Thursday.